Okay, so yeah, I'm going to talk about a super simple model to try and investigate the issue of how a planet can maintain its habitability over billions of years. So yeah, the problem of interest here is not about whether a planet can be instantaneously habitable, but whether it can stay that way for a very long time. And why would we care about that problem? Well, fairly obviously, we wouldn't be here today if Earth hadn't had uninterrupted habitability over 3 or 4 billion years or so. And likewise, for extraterrestrial intelligence, that probably would also rely on a very prolonged period of habitability for evolution to progress as far as intelligence. And as some of the speakers have mentioned, it's rather surprising that Earth stayed habitable for that long. This phenomenon is non-trivial. So we know about the fate young sun paradox, that the early oceans should have frozen or else the late oceans should have boiled away. We can also look at the residence time of carbon in the Earth's surface system, so the ocean's atmosphere and soils, and that is extremely short relative to billions of years. So there's plenty of potential for the atmospheric CO2 to empty or increase to very high levels within that timescale. We can also obviously look at the surface temperatures of Mars and Venus, and they're not conducive to liquid water. But also, it's thought that Mars had surface water at the beginning of its history or early on in its history, and perhaps Venus also. So I think it was said earlier on that perhaps habitability is something that's extremely fragile, and it's rather remarkable that Earth managed to keep it for so long. If so, how did it do it? I think this is something that's very interesting, but it's also something that's very hard to study. Obviously, we don't have a lot of observations extending over billions of years. We can't do experiments over billions of years on planets or anything. We can't really, it's not very easy to study this sort of problem, or at least the persistence of habitability with complex climate models because of the runtimes involved. So therefore, I think we can perhaps the best way of trying to sort of make headway with this sort of problem, or at least learn something about persistent habitability, is to try simple models. And I'm going to show you an extremely simple one. And this is a little bit similar to what Colin was showing with some of his diagrams in terms of what the axes are here. You're probably not, maybe you are familiar with this sort of thing, maybe you're not, but I'm just going to step through explaining what's going on, what the features are on these plots, and what the axes are. Fairly obviously, the x-axis on these plots is the average surface planetary temperature, and we have to specify some range that's habitable, so when it gets too cold or when it gets too hot for life. The y-axis on all of these is the rate of change of temperature with time. So fairly obviously, if you're above the x-axis, we're talking about positive rate of change of temperature. The planet is warming up over time. Below the x-axis, it's cooling down. And I shouldn't be calling it the solar constant, but I am again. So if we just plot the heat input from the sun on this sort of scheme, we would have a constant, certainly at the top of the atmosphere, we would have a constant amount of temperature received on the planet regardless of what the planet's temperature is. So we would plot that as a positive line with, which is just a flat line. If we're to consider the black body radiation, so a planet without an atmosphere, then the outgoing long-wave radiation is going to be proportional to the fourth power of the temperature in kelvins. And we're losing heat from the planet, so it should be below the x-axis, and it should be increasingly negative as we get to higher temperatures. I don't know exactly how one should plot on the Ice-Albedo feedback on here. We're talking about the average planetary temperature, so we can have ice at temperatures above zero, but in some way we're going to have an increasing loss of heat from the planet, or at least failure to receive all of the sun's insolation at lower temperatures. And likewise on Earth and other watery planets, there'll be the temperature water vapor feedback, whereby we retain more of the heat that's coming in because we have more water vapor in the atmosphere at higher temperatures. So this is just to give you the idea that there are lots of different processes and feedbacks that operate on Earth and on other planets. We don't know exactly how exactly what feedbacks are operating on Earth, for instance, and we don't know what the sum of those, or the combined effect of all of those processes and feedbacks is. But that's what I'm going to be looking at in this model, not the individual processes and feedbacks in the radiative budget, but the combined effect, the total effect of all of them for the planet. So that's what I'm talking about with these sorts of plots then, and this is showing here an example for some randomly generated planet of what it might be in terms of the tendency to warm up or cool down at different temperatures. And I should say that the other thing that I've done with this is that I've just come up with a very simple procedure for randomly generating a whole zoo of different planets in a random way. And you can do this in different ways. I'm just going to say the way that I did it for the standard version is to randomly determine a number of nodes between 2 and 20 across the habitable range and then space them equally. But you can do it, you can space them randomly, you can do it in different ways. And then again, using a random number generator, just determining in that way whether for each node, whether there's a warming or cooling tendency and what the magnitude of that is. And then interpolate between the different nodes to specify the warming or cooling tendency at different temperatures between the nodes. So that's the procedure for randomly generating a whole diversity of different planets. And it throws up lots of different types of planets. Some of those have zones of runaway cooling. So obviously if you have a tendency to cool down towards the lower end of the habitable range, you're going to zoom off to lose habitability, zone of runaway warming, etc. So this just emerges out of this way of doing things. But you can also get planets with different basins of attraction. So each of these red boxes here is a basin of attraction. So we have a zero crossing point here. This is an attractor temperature. And you can see here within that box at temperatures above the attractor temperature, you've got cooling, so you'll come back towards that temperature. Temperatures below, you've got warming, so you're going to again migrate towards that attractor temperature. So this system just throws up zones of runaway cooling and runaway warming for some planets and basins of attraction as well. And the other feature of creating a planet randomly is to give it some sort of long-term forcing to represent, for instance, the changes in stellar luminosity over time. So that's the procedure for randomly generating different planets. And I'm going to show you in a minute just this model running through time. It goes quite quickly. So before I do that, I'm just going to help you understand what's being shown here. So on the top left of here, we have the initial state of the tendencies for warming or cooling at different temperatures. That's the initial state of the system. And at the bottom, we have the final version after the long-term forcing has been applied for 3 billion years. If the planet gets that far, and then in the middle we just have the state at one particular point in time. And on the right hand side here we have what actually happens when you run this particular planet from a random initial temperature. So this is the evolution of temperature on that planet. So we have time on the x-axis, temperature on the y-axis. And then down here we have different random perturbations again that are applied that can knock the planet out of basins of attraction, for instance. So this is just showing you the model running. This is the speed at which the model runs when you spin it, when you put it on a normal sort of PC. And you can see that it skips through different planets really quite quickly. Most of the planets that get randomly generated have no potential for maintaining habitability, and they very rapidly become uninhabitable. A few of them stay habitable for a short time and then go uninhabitable. And occasionally you get planets that stay habitable for longer durations and sometimes 3 billion years. And so I think this is quite interesting that you can just generate a zoo of different planets and you can quite quickly evaluate their tendencies to stay habitable or to run off to uninhabitability. And this last one here you can see stayed inhabitable for 350 million years, and I didn't run it out for any longer just for the purposes of time. So it's an extremely simple model, but I think it allows us to do some work towards understanding the persistence of habitability. But you could say, so what? We don't know a lot about exoplanets in order to be able to decide whether such a model is at all realistic. And it's also an extremely simple model. So why should we have any credence at all to the results that come out? Well, I think there is some hope. There is one way that we can hope to get around that, which is by not just looking at one particular model variant, but generating a whole different collection of model variants where we alter the parameter values, we alter the structural assumptions in the model, and then we try and search for model results that appear regardless of your parameter values or your structural assumptions. And I think those are the most interesting results, those ones that are robust and independent of the model details. And I'll just show a couple. I haven't really got too far with applying this to all sorts of different problems, but one thing that stares out of the runs that you do is that if you don't have any attractors, you've got no chance of staying habitable. So this is the frequency distribution of the planets that are thrown up by this random generation procedure in terms of the number of stable attractors. And this is the corresponding frequency distribution for those planets that only those planets that ever have a chance of staying habitable. And you can see for those planets with no stable attractors, they don't stay habitable. So random walks just don't work for in this simulation. They never stay habitable. Another interesting result, I think, is that for this particular plot, 100,000 different planets were randomly generated and then each run 100 times with different random perturbations. And you can see the results in blue here. This is only showing those planets that were successful at least once out of those 100 times. So all of the planets that were always unsuccessful are not shown here. And on the x-axis here, we have the number of successes out of 100 for those successful planets. And what you can see here is that the large majority of the planets that were sometimes successful were only very infrequently successful. So most of those planets that were sometimes successful were successful probably less than 10% of the time. And only a very few of them were successful a large majority of the time. So that, I think, is quite interesting if you take that finding, which is quite robust, as I said, out of lots of different variants of the model, and then you try to think about what does that mean for Earth's persistent habitability. So if you think that that does apply to Earth, then you'd say that Earth was almost certainly not guaranteed to stay habitable at the outset. So if you were to go back to the Archean and you try to predict whether Earth would have stayed habitable, you would then conclude, if this is right at least, that more than likely Earth would not have done, but there must have been a large element of chance and good fortune that Earth did stay habitable. Okay, so those are my conclusions, and I'll leave those up, and you can get the code if you're interested from the address shown there. Thank you.
We have time for questions.
I know you said that you haven't taken a look at a lot of different kinds of planets yet, but do you have an idea of the statistics of what dictates like a long-term habitability in this model? Do you have any idea of some trends that'll pop out? Maybe you can identify early on and say, oh, this one has a good chance. Yeah.
Yeah, as I said, number of stable attractors is one thing. The fraction of the habitable range that's occupied by runaway feedback zones, obviously if you have a lot of that, then because the initial temperature is randomly determined again for these, you'll have a greater chance of running away. Other things are, for instance, whether the position of the attractor is towards the edge of the basin of attraction. If it is, it's more likely to get knocked out by perturbations into either a runaway feedback zone or another attractor. So what you want are large attractors where large basins of attraction where the attractor point is fairly central to that large basin. And then obviously things like the sizes of perturbations, but they're varied for each of the different runs.
Any other questions? No, right behind you.
What if you put in your model something that was alive and then you let it promote the conditions that kept it there?
Okay, so this model doesn't distinguish between abiotic and biotic processes, as you'll have understood. Obviously, I've actually written a book about whether I think the Gaia hypothesis is a good way of understanding things or not, and I concluded that it wasn't. But that's not to say that biological processes didn't have an effect. They obviously had an effect on whether Earth stayed habitable or not. But yeah, so I think whether you were to put something that was alive in there, whether that would assist habitability or not, I would say from my perspective that it might assist keeping habitability, or it might not. It could go either way. I would have said, obviously, Gaia proponents would suggest that life tends to promote habitability, but I haven't seen evidence for that on the whole. Yeah.